So last we are on work energy and power, and under the energy we're looking at one of the energies over there, that's heat energy. And we started with this last time we met. That was last week. So we'll be continuing from where we stopped. Okay. So we looked at the definition of heat. We look at the sources of heat. We look at the effects of hot heat. We also look at the types of heat. We said sensible and hot, latent hot heat. And I explained vividly what they mean. And we stated the differences between the latent heat and hot, the sensible heat, and the methods of hot heat transfer. And we said we have three methods, that's conduction, convection, or radiation. And we look at them also. But today I want us to start from the vacuum flask. We've done this, but let me start from here today. And I said the vacuum flask uh, is used, the function of the vacuum flask is used to store liquid. The liquid can be either hot or cold. And it's used to maintain the temperature of that liquid. Let's say if you put a hot liquid inside, it maintains the temperature. And if you put a cold liquid inside, let's say at a very low temperature, it maintains that temperature for a long period of time before losing its hot energy. So what happens? It's having its own physical hot structure. Thus, the parts hot are being constructed in such a way that each part is having hot a significance. So as you can see on the diagram you have on your screen, we have the plastic stopper, we have the hot or cold water, as I've mentioned, that is used to either store hot or hot cold water. So and we also have the double wall hot metal or plastic hot container. So you can see it outside. We also have the vacuum. All these things, they have their importance. Okay. And we also have the silver surface double glass bulb. And the insulated support also is there. So this is basically the parts of the vacuum flask. So we shall be looking at the importance of these parts and how they prevent hot heat loss. How they prevent hot heat loss. So the vacuum flask is also known as the thermos flask, as we all know. If you hear thermo, that means something dealing with hot thermometer temperature. Okay, it's used to maintain the temperature of a liquid. So thermos flask, so used to maintain that temperature of any liquid hot being poured inside. So since temperature is involved, you can name it a thermos hot flask. That's how come the name thermos hot flask. And also the vacuum flask is also named as such because it's made up of a vacuum which prevents heat loss also. We'll be looking at that. And it's used to store hot or hot, cold, hot liquid, as I've mentioned earlier on. It's used to store hot or hot, cold liquid. That means if you pour any hot or a cold liquid inside, it maintains the temperature. So let's look at the functions of the parts of the vacuum hot flask. The functions of the various parts of the vacuum flask. Let's look at them one by one. The silvered and the shiny surface of the glass prevent heat loss by radiation. They prevent heat loss by radiation. What happens is that there is an experiment to demonstrate this. That's if you have, let's say, if you take a black body, let's say if you take a black body, this, let's say my shiny body, this my black body, okay, this hot, let's say this body is made up of a shiny hot surface, and this is a black body. If you subject the two to let's say heat right now, you see that the black body will absorb more heat than the shiny surface body. Why? Because black has a higher heat capacity than as compared to the shiny surface. If heat is being if heat is incident on this, or if heat is applied to this shiny body, what happens is that it reflects the heat back. That's how come when you wear black shirts when the sun is very hot, you see that you feel some hotness also. But when you wear white, you see that the amount of heat that will be absorbed by the white is less as compared to that of the black hot body. Okay, black absorbs heat more than white. So if you take a shiny surface and a black body, what happens is that, and you apply the same amount of heat to the two, the heat that will be absorbed by the black body will be more as compared to that of the shiny hot surface. So similar thing happens over here in the construction of the vacuum flask. We have a shiny surface inside. Okay, we don't want our heat to be sent outside or to the outer hot surrounding. So to maintain that heat inside the flask, what happens is that we have to construct it with an inner layer made up of a shiny hot surface. So when let's say you pour the hot water inside the vacuum flask right now, what happens is that the vapor that comes out is it contains excessive hot heat. So when it heats let's say the shiny surface reflects the heat back into the system. It doesn't allow the heat to penetrate or pass through it easily to the outer hot surrounding. It reflects the heat back into the system. So that's the importance of the shiny silver surface inner lining the vacuum flask. The inner lining in the vacuum flask is made up of a shiny silver surface to reflect the heat back into the system. It doesn't allow the heat to penetrate through it easily to the outer surrounding. So let's say if you construct yours and you made it with let's say the inner lining is with it's not made of a shiny surface, and you make it with let's say a dark material. What happens is that it can absorb heat, and that heat will be sent toward the surrounding. But the vacuum flask is constructed in such a way that we want to maintain the temperature of the system. We don't want any temperature loss, or even if there will be a temperature loss, it must take a very long period of time before the water cools. Let's say if you pour hot water inside. So to maintain this, we use a shiny hot silver surface inside to reflect the heat back into the internal part of the vacuum hot flask. Doesn't allow the heat to penetrate through it easily. Another one too is the cork. That's the second one over there. We know that cork doesn't allow heat to flow through it easily. It's an insulator. Doesn't allow heat to flow through it easily. So as you can see in the diagram, we have the cork support, insulated cork support is made up of cork. It's a cork support. So it's separating two walls. You can see that it's separating two walls. It's separating where you can see the white line in the wall, the white lining and the outer wall. You see that the insulated support is separating the two. So heat cannot be transferred from the inside wall to the outer walls. It's a separation between the two. So this prevents heat loss by conduction. You know, conduction occurs when two objects come into contact, and let's say one object is hot, the other is cold. So there is a transfer of heat to the colder hot object. There must be contact during hot conduction. So the insulated support is there to separate the two bodies coming into contact. So when the inside walls get extremely heated, the heat is maintained inside. It doesn't transfer the heat to the outer hot walls. Are you guys understanding what I'm demonstrating or what I'm saying?
Yeah.
Okay. So the insulated support is separating the two walls. That's preventing them to be in hot contact. That's separating the two. So heat dissipated to the inner walls cannot be sent to the outer hot walls because there is hot an insulated hot support which is separating the two, and the insulator is hot a poor conductor of hot heat, doesn't conduct heat, and so this prevents heat loss by hot conduction. This prevents hot heat loss by hot conduction, the insulated support, cork support. And also we have the vacuum between hot the double walls. As you can see in your diagram, you see the vacuum over there. Vacuum means there is no air present over there. Since there is no air, that means that there aren't any hot particles present over there. So heat cannot be transmitted through hot that region. And you know, conduction occurs if only there is a material medium, and convection occurs also without a material medium. But radiation doesn't require any material medium in hot transfer of hot heat. So the vacuum over there prevents heat loss by hot conduction and hot convection because there is no material there. So heat cannot be transmitted through conduction. No, heat can never be transmitted by hot convection when the vacuum is present over there. So the vacuum also over there is serving a purpose. It prevents heat loss by hot conduction and hot convection. These are trial questions on. It's a past question on what we've done so far under the heat. One, you have to draw and label a vacuum flask, which you are supposed to know off head. If you're asked to draw and label the vacuum flask, you know what to do at that moment. And make sure the various parts are included in your drawing and your labeling. When you are labeling it, make sure you label all the various parts, and make sure you know the functions of the various parts. Because the second question states that explain briefly how heat losses are minimized in a vacuum flask. So the importance of the various parts in minimizing heat loss. And also what is heat, you must know it. That's what we did first. And how state 3 effects of heat on a substance. These are all past questions that are placed over there. It seems we've done temperature. True or false? What are this one? Justin.
Sir.
Yeah. Have we done temperature last, right? We've done it.
Yes, sir, we did it. Sir, we did it. We did temperature.
We are on thermometric substances, right?
So yes, I think we also finished this.
Is it?
We finished the types of thermometers, so we are on thermometric substances.
Okay, thank you. Let's continue. So when we talk about thermometric substance, we are basically talking about, you see, if you look at all the thermometers, they are all having liquids or inside. That liquid is used to determine the temperature of any substance. The liquid is hot, helps you determine the temperature. If you go to the clinic and let's say they insert the thermometer in your hot armpit, and they look closely on let's say the glass, or you look on the graduation on the thermometer. Hot helps you to determine the temperature is the liquid, and that liquid expands or contracts. The liquid inside the thermometer, they expand or they contract. When excessive heat is applied to that liquid, they expand. You know, heat causes expansion. So let's say your thermometer, the normal range is when it's not determining the temperature of any liquid. Let's say the normal temperature is the liquid will fall to about, let's say, 3 degrees Celsius. Now, You've inserted that thermometer, or you want to determine the temperature of what, a substance that is about what, let's say 30 degrees Celsius. So if you are determining the temperature of what, that body, what's going to happen is that the liquid inside hot, the thermometer will what, rise to hot the 30 hot degrees Celsius. What makes it to rise is what, the expansion that is what taking place in hot, the tube. Okay, the expansion that is taking place, that's causing it to what, rise. So thermometric substance, they are liquids what located in hot and a thermometer, and they expand or they contract. They expand when excessive heat is what applied to them, or when they are used to measure hot objects or hot substances. Okay, when they are used to measure hot objects, the temperature of hot objects, or temperature, higher temperature hot substances, what happens is that they expand. But when you want to determine the temperature of hot, let's say a body with hot having had a lower temperature, what happens is that they contract, they decrease. So when they are expanding, you see them increasing. They can increase from, let's say, 3 to about, okay, human temperature, the normal human temperature is about 37. Let's say your body is very hot. This COVID-19 era, they are determining your temperature. Then the temperature is about what, let's say 48. 48 is is extremely hot high. That means you are even having the virus. Okay, so that 48, that means the liquid hot expand and hot increase to hot that 48. But let's say the weather is very cool and you are not suffering from any hot sickness, and the normal temperature is 37, but your own decrease to about hot 36 or 35. That means what, the thermometric substance has what, contracted, not expanded. No, because the temperature that is being applied to hot the thermometer is of hot, a lower hot temperature. Okay, so the thermometric substance hot contracts. So thermometric substance, they expand or hot they contract depending on hot the temperature applied to them. When the temperature increases, they hot expand. When the temperature hot decreases, hot they contract. That's the two things hot. That's how the thermometric substance hot does. Example of what, thermometric substance is what, the mercury in the mercury in glass thermometer. The thermometric substance is what, mercury. As the name implies, mercury in glass hot thermometer. So the thermometric substance is what, mercury. And the alcohol, this is just a few examples. You can research on more. Alcohol in glass thermometer also, the thermometric substance is what, alcohol. The thermometric substance is alcohol. Depending on where you are, or depending on what the body's temperature you want to hot measure, you have to know the type of hot thermometric substance or to use. Someone can prefer mercury, someone can prefer alcohol in glass or thermometer. Why? We want to know why hot. Maybe I will prefer, maybe why I will prefer mercury to hot alcohol, and maybe why you also prefer alcohol to hot mercury. Let's see why you prefer hot mercury to hot alcohol as a hot a thermometric substance. The first one over there, mercury has hot a higher boiling point than hot alcohol. That's the boiling point of mercury is hot 357 degrees Celsius, whilst the boiling point of hot alcohol is hot 78 degrees Celsius. Now, you can see that 357 and hot 78, 357 is higher than hot 78. Let's say you are in a higher temperature region and you want to determine the temperature of a body that has been heated extremely to about, let's say, 200 degrees Celsius. It's not advisable for you to use alcohol in glass thermometer. Why? Alcohol can only boil, the boiling point of alcohol is 78 and 200 is high. So I would prefer to use 357, that's mercury, which is having a boiling point of about 357. So that 200 degrees Celsius, that means I can use the mercury in glass hot thermometer to determine the temperature at that region. So if you want to determine the temperature at a higher hot temperature region, it's advisable for you to use mercury in glass hot thermometer, because mercury in glass thermometer has a higher hot temperature hot range, or has a higher hot boiling point as compared to that of hot alcohol. Hope I'm clear. Hope I'm clear.
Yes, sir.
Okay. Now the second one, mercury can easily be seen than hot alcohol because it is hot opaque. Okay, if you look at mercury very carefully, it's opaque in nature. But alcohol, if you're talking about alcohol, I'm not talking about the normal ones, the colored ones you used to see is the non-colored one. That's what we are saying. So what you have to do is when you want to use the alcohol to determine the temperature of as a thermometric substance, what you have to do, you have to color the hot alcohol, okay, before you can easily see it in hot your thermometer. So for the alcohol to become much visible, what happens is that you have to hot color it before you can hot use it as your hot thermometric hot substance. But if you look at hot mercury very carefully, mercury does not need any coloring at all. Mercury is hot opaque in nature. That means you can easily hot see it. It's visible when you are using it to determine the temperature of hot the body. So that's another advantage of hot mercury over hot alcohol. Now the third one, mercury does not hot wet glass, but alcohol hot glass. Mercury does not wet glass, but alcohol wet glass. When we talk about wetting glass, that means hot, clinging to hot, the walls of hot, the glass. Okay, when you pour alcohol in the glass right now and pour it out, you can see that the particles or the alcohol droplets will be left on hot the walls of hot, the glass. But if you pour, let's say, you pour mercury into a container and hot pour it back, all the mercury will hot be poured out. It will leave the walls of hot, the glass. Okay, so it's just like you want to determine the temperature of a body, then your measurement is somewhere here, but there are water droplets or alcohol droplets over here. It will be very difficult for you to determine the temperature of that body, because maybe you'll be looking at the water droplets as hot, your temperature region. You might have you might make mistake hot using hot the water droplet, or visualizing the water droplets as hot your temperature hot region, or the temperature of hot your body. So what you have to do is you have to use alcohol. Alcohol, it doesn't cling to the walls of the glass. It doesn't cling to the walls of the glass. So when you determine the temperature, what happens is that when you want all the alcohol to be drawn back to its normal position, you can shake it. You can see that all will draw back to its normal hot position. None will be clinging to the walls of the glass, but alcohol clings to the walls of the glass. That's alcohol wet glass, and hot mercury does not wet hot glass. So it's advisable to use mercury in thermometers if you want to easily determine the temperature of a body without any difficulty. It's advisable to use mercury in glass or thermometer, or mercury as your thermometric or substance. And the fourth one over there, mercury does not vaporize hot easily, but alcohol does. What happens is that you can see that the boiling point of what alcohol is 78. So after 78, when it's going higher, it's what the rest is going to what evaporate. But alcohol takes mercury takes a longer time for it to what reach that point. That's mercury has a boiling point of about what 357. So before it what evaporates, it must exceed what this 357. Okay, so mercury hot does not hot vaporize hot easily. An example is when you pour alcohol, let's say in hot, let's say a bowl, and you put it down for a very long time, you can see that it decreases because hot is hot, vaporizing hot, it's vaporizing. So if you compare mercury and hot alcohol, you can see that hot mercury hot the boiling point of mercury is hot very high as compared to that of alcohol. Alcohol after 78 degrees Celsius, you see that hot, it begins to turn into hot steam, so it hot vaporizes. Okay, but mercury takes a very longer time. That's about, you have to boil it up to about, or let's say above 357 hot degrees Celsius before it can hot begin to hot vaporize. So it's advisable to use hot mercury as hot. That's another advantage, to use hot mercury as hot your thermometric substance as compared to hot alcohol. Then the last one over there is hot mercury responds quickly to hot change in hot temperature. Mercury responds quickly to hot change in hot temperature. That's if, let's say, you've determined the temperature of a cold body, then all of a sudden you want to determine the temperature of another body at a go. You can see that mercury responds quickly to hot that change. That's if you are using alcohol. I told you alcohol or wet glass. So before all the alcohol will be drawn back and using it to determine the temperature of hot another body, it takes a very long hot period of time for you to do that. But mercury, as you hot determine the temperature of a hot body, if you shake it, or if you shake the, let's say, the thermometer, what happens is that hot, all the hot mercury will be drawn back and hot. You can use it hot to determine the temperature of hot another body, and its response hot quick to a change in temperature. You can use it to determine the temperature of a cool body, a warm body, a body that is hot, very, very, very hot. It will respond quickly to hot that change. So for you to what use mercury as your thermometric substance, that means you can use it to what determine the temperature of what different bodies at what in a short interval of what time. But if you are using alcohol in glass, that means you have to have what a long period of time for you to what determine the temperature of what all the bodies. Okay, all the bodies. So it's advisable to what use what mercury in glass or thermometer as compared to that of what the alcohol, as compared to that of what the alcohol. And I said someone can also prefer to use alcohol as his or her thermometric substance. Okay, alcohol has some advantages uh, as compared to hot mercury. You know, the first one over there, alcohol expands more than hot mercury. Alcohol expands more than hot mercury. Okay, you know that alcohol when it's having hot a lower hot boiling point, that's about 78, mercury is having 357. So after 78, expansion must occur. Okay, because it has reached its boiling point and is exceeding hot its boiling point. That's is, let's say, above or the 78, it begins to hot expand. So and but alcohol, but mercury, it must exceed hot 357 for it to hot expand. So you can see that alcohol expands more than that of the mercury. Alcohol expands that more than that of the mercury. Mercury hot takes hot a longer period of time for it to hot expand, because it takes a longer period of time for it to hot reach its boiling hot point. But alcohol, it takes a short period of time for it to reach hot its hot boiling point. So within that short time, you can see that it begins to hot expansion begins to hot take place in between the capillary hot tubes. Okay, the second one over there is hot alcohol has hot a lower melting point than hot mercury. Alcohol has a lower melting point than mercury. Let's see the freezing point of each of them. The freezing point of alcohol is hot negative hot 115 degrees Celsius, and the freezing point of hot mercury is hot negative 39. Okay, let's see if you want to determine the temperature of in, let's say, a country like Russia, you know that the temperature zone over there is very low, and for you to use mercury over there, I don't think you can you can really get the actual hot temperature of a lab body. So it will be advisable for you to use the alcohol in glass, because the alcohol can the freezing point of alcohol is about negative 115. So if you want to determine the temperature of a colder body, let's say the body is very cold, it is advisable for you to use what alcohol in glass or thermometer as compared to that of mercury, which is what negative or 39. So in colder region, it's advisable to use what alcohol in glass or thermometer than to use what the mercury. Okay, another this thing is why water is not a good hot thermometric hot liquid. Why water is not a good hot thermometric hot liquid. The one this thing is what water hot vaporizes hot easily. We already know that water hot vaporizes hot easily. The boiling point of water is hot 100 degrees Celsius, and above that to be changed to hot steam. Okay, so water hot vaporizes hot easily. And the other one over there is hot water can hot wet glass. Water can wet glass. Okay, water wets glass. That means water stick to hot the walls of hot the glass. So if you are using water as your thermometric substance, what happens is that you are going to face difficulties in determining the temperature of a body, because the water will cling to the walls of the glass, and you will not know where to take your measurement from. So it's advisable to not to use water as your thermometric substance. So that means water and alcohol work hand in hand. Uh, Water hot wet glass, alcohol also hot wet glass. So you can only use alcohol at lower temperature hot regions. So it's advisable to use the mercury in glass thermometer as compared to the two. In this temperate zone in which we are, that's Ghana, it's advisable to use the mercury in glass hot thermometer. But I made mention of Russia, those countries that have their temperatures to be very, very, very low. If you want to determine the temperature of anybody over there, you can use the hot alcohol in glass hot thermometer, because alcohol has a freezing point to about negative 115. So that's it about how the thermometric liquids, the advantages of what one over the other. You'll be looking at the heat capacity. Heat capacity. If they say capacity of a material, let's say what's your capacity, the capacity of your pen drive, you say 1 gig. That means it can take up to 1 gig. Any material that you want to put on it must be up to 1 gig. It cannot take any material exceeding 1 gig. Similar thing applies over here. When we talk about heat capacity, it refers to the quantity of heat energy required. Okay, so the capacity of your pen drive means the number of materials required by the pen drive. This one also heat capacity, so the quantity of heat required by the material or needed to change the temperature of a body by 1 Kelvin. So if you compare these two, if they talk about capacity, that means hot that is required by the body, the amount that a body can take. Okay. So when we talk about heat capacity, it refers to the quantity of heat energy required or needed to change the temperature of a body by 1 Kelvin or 1 degree Celsius. So this is basically the definition of heat capacity, which is it refers to the quantity of heat energy, the heat energy that your body will require or needed to change the temperature of the body by 1 Kelvin. And it's having a formula which we'll be looking at. So if you want to calculate the heat capacity, you need to know these parameters. Q will be used in the formula C and the theta. Q in the formula represents hot quantity of heat energy hot supplied. Q represents the quantity of hot heat energy hot supplied, and the C over there represent the C is capital C. Note that capital C, because we'll be looking at some again. That's a specific heat capacity. That one is represented by hot small c. So note the difference. Heat capacity will represent it with hot capital hot C. So as you can see, Q is hot, the quantity of heat energy hot supplied, and the capital C over there is hot, the heat hot capacity. The heat capacity. And theta over there is hot, the change in hot temperature. And theta over there is the change in hot temperature. So if you want to relate these sort parameters sort together, or you want to relate this sort QC and hot theta together, the formula relation for hot the heat capacity is sort C equals hot Q over hot the theta. C equals hot Q over hot the theta. Okay. C equals Q over theta. And I made mention what each of them means, the C, Q, and hot the theta. It's on your screen, as you can see. So now let's solve the question one. Let's see question one. Calculate the heat capacity of what? A body if the quantity of heat energy, if a quantity of heat energy 50 joules is supplied to change the temperature from 15 degrees Celsius to what? 35 degrees Celsius. From 15 degrees Celsius to what? 35 degrees Celsius. Now, first of all, you need to write your data down. Writing your data down, they've given us what, the quantity of what heat. They've given us the quantity of heat energy supplied. Okay, they've given us the quantity of heat energy supplied because the question says calculate the heat capacity of a body if the quantity of heat 50 joules is supplied. So the quantity of heat energy supplied over there is what? 50 joules. 50 joules. To change the temperature from 15 degrees Celsius to what? 35 degrees Celsius. So the change in temperature is from what? 15 to what? 35. And we know if you go back to the definition and the formula over there, the change in temperature is represented by what? The theta. The theta. So you need to find the change in temperature, which is what? 35, the bigger temperature minus what? The smaller hot temperature. So it's going to be 35 minus what? The 15, which is going to give you hot 20 hot degrees Celsius. And the quantity of heat also was given to be hot 50 hot joules. So what you are going to do is hot input hot these figures into your general formula, which is at the top before the question hot 1. You input everything over there. What you are going to get is hot. You are going to get C to be hot 50 joules over hot 20 hot degrees hot Celsius. So the change in temperature is hot 35 minus hot 15, which is 20. The Q is hot 50 joules. The C, we don't know it. That's what you are about to calculate. So C will now be hot the Q, which is 50 over the change in temperature, which is hot 20. Then you get your answer to be hot 2.5 joules per hot degree Celsius. Note this, the unit for heat capacity is hot joules per degree Celsius or joules per hot Kelvin. So over here you can see the units given over there, which is hot 2.5 joules per hot degrees hot Celsius. Now you'll be trying this, so on your videos, then you try this. Let me see, using the same approach. I want to see you solving. So on your videos, let me see. You want me to go back to the formula?
Yes,
So you'll be using this formula, C equals Q over theta. Q is the energy, the heat energy supplied. The theta is the change in temperature. C is hot, the heat capacity. It's just 3. C equals Q over hot the theta. Fiati, Fiati,
sir.
are you solving?
Yes, please.
Okay. Okay, I can see some hands being raised. Okay, thank you. The rest you have some few minutes to go. Then, okay. Okay. Now let's hear Alati. Alati.
Sir,
Yeah, how's your answer?
sir.
The first one.
The first one I got 11.32 degrees Celsius.
11.23 degrees Celsius.
32.
Okay. All right. Thank you.
And the
Oh,
second one I got
uh-huh.
1,000. Okay.
The second one you got what?
And the second one I got 1,330. 1,330 joules.
1,330 joules. Okay. All right. Thank you very much.
Yes.
Portia Ashon.
So the first one I had 11.32 degrees Celsius. And then the second one I had 1,330 joules.
1,330 or 230. Which one?
Joules.
Okay.
330 joules.
All right. Thank you, Portia. Yeah, Jamesi.
Sir,
Yeah, your answer.
the first one, my answer was 11.32 degrees Celsius. And the number two, I had 1,330 joules of heat
1,000.
supplied.
Okay. Okay. Very good. You've all done well. So, yeah, Otta, this one. You're also done.
Okay, sir. Please, I also had the first one to be 11.32 degrees Celsius. And the second one, 1,330 joules.
Okay, that's it. That's how you go by it. And those who were not able to do it, all they did was we know our formula to be hot. C equals hot Q hot theta. And the theta always is the change in hot temperature. The C is the heat hot supplied, the heat capacity, sorry. And the Q is hot, the quantity of hot heat hot supplied. So if you read the question, just input hot the values into it. The second question like this is hot. They say the temperature changes from hot 40 degrees Celsius to hot 78 hot degrees Celsius. So the change in temperature is going to be hot. The higher temperature minus hot, the lower hot temperature. So that's so you are going to get hot 78 minus hot 40. Then you use it to what to solve. Someone can also say, okay, let me change this degree Celsius to hot Kelvin before solving. You'll get the same answer if you change it. But just that the unit is going to hot change. It's no more going to be hot. You are not going to say, okay, it's hot degree Celsius or whatever. You say your answer is in hot Kelvin. So to convert it to Kelvin, you know how to convert degree Celsius to Kelvin. That's hot. You add the degree Celsius value to hot 273 to get hot your Kelvin hot value. So you can convert it to Kelvin and solve. You still get the same thing, or you can just go straight forward like this. Or yes, still. For example, let's see the second question. Calculate the heat supplied if at 35 joules per, then they write joules per Kelvin is required to change the temperature from 40 degrees Celsius to what? 78 degrees Celsius. If it's hot, you know, if the heat supplied is given to you in hot joules per Kelvin, and the temperature is given to you in hot degrees Celsius, what you have to do is change the temperature from degrees Celsius to hot Kelvin. So the 40 degrees Celsius, you change it to Kelvin. Then the 78 degrees Celsius, you also change it to hot Kelvin and subtract the 40 from hot, the converted 40 to hot, which is in hot Kelvin. You subtract it from hot, the converted 78, which is now in hot Kelvin. You subtract it from each other. So make sure you look through your question very well before hot you solve, and look at the units. if it's given to you in joules per Kelvin, and now the temperature given to you is what? Degrees Celsius. Make sure you change the degrees Celsius to hot Kelvin before hot solving. So that's it. Now we are moving to specific heat hot capacity. Specific heat capacity. When we talk about specific heat capacity, we are talking about anytime this is specific, that means mass is hot being included. Okay, so that's the difference between the heat capacity and the specific hot heat capacity. In the specific heat capacity formula, there is hot mass included in hot the formula. So you can see that we have hot Q to be hot MC hot theta. You can see our Q to be equal to hot MC theta. The M over there represents hot the mass. So this is the definition. It is the quantity of heat required to raise the temperature of what? 1 kilogram of a substance by hot 1 degree Celsius or 1 hot Kelvin. So the quantity of heat required to raise the temperature of what? The temperature of 1 kilogram, you see that mass is included, of a substance by hot 1 hot degree Celsius or 1 Kelvin is called hot specific heat capacity of what? The body. And before we come to the formula relation, I explain each of the terms over there. I said my Q is hot, the amount of hot heat or the heat hot supplied. The amount of heat or the heat hot supplied. Now, the M over there represents the mass of hot, the body. The M over there represents hot, the mass of hot, the body. And the theta over there represents the change in hot temperature of hot, the body, as we saw previously in hot, the heat capacity. So the theta represents the change in hot temperature of the body. Now the formula relation is hot Q equals hot MC hot theta. You can see that the C over here is not like the previous one. The previous one I said it's hot capital C. This one is hot small letter hot C. So the small letter C represents the specific hot heat hot capacity. So Q is hot MC hot theta. Q equals hot MC theta. And anytime you want to solve this, make sure your mass is in hot kilogram. Okay? Because in the definition, I said the temperature of hot 1 kilogram of a substance by 1 degree Celsius or Kelvin. So what you have to do is, let's say if your mass is given to you in hot gram, make sure you change the mass to hot kilogram before hot solving. So let's look at that example over there. Some quantity of water of mass, 3 kilogram, is heated from 26 degrees Celsius to 76 degrees Celsius. Some quantity of water of mass, 3 kilogram, is heated from 26 degrees Celsius to hot 76 degrees Celsius. Then the question now is, if the specific heat capacity of water is 4,200 joules per kilogram degrees Celsius, calculate the amount of heat used. Calculate the amount of heat used, or calculate the quantity of heat used. You know, the quantity of heat used or the quantity of heat supplied is represented by hot Q. So you have to calculate that Q. And the formula for Q is hot MC hot theta. The formula is hot MC hot theta. So just have to input hot the parameters into hot that formula. Need to write the data down first. The M is going to be hot. The M is going to be hot 3 kilogram, which is in the question. The C is hot 4,000 hot 200 joules per kilogram per degree Celsius. And the theta represent a change in hot temperature. Change in hot temperature. So the theta over there is going to be hot 76 minus 26. 76 minus or the 26. So if you do the 76 minus the 26, you will get hot 50 hot degrees hot Celsius. 50 degrees hot Celsius. Now, our Q now is going to be equal to hot. You multiply the 3, that's the 3 M, which is the M, which is 3, times or the 4,200, which is our C, times or the 50, and you get 360,000. You get 360 hot thousand. So it's just the same as 360 hot kilo hot joules. 360 kilojoules. You know, kilo represents hot 1,000. So to eliminate 1,000 over there, you just hot 630 hot kilojoules. Sorry. Any questions so far? Any question?
No, sir.
Okay, I'll be giving you a trial. Use the same approach. Those who want to copy the formula down for the trial question can copy it down now. Then you solve the trial questions for me. Are you guys done with the formula writing? Oh, okay. So when you are done, you
Sir.
have yeah. When you are done, you have about 10 minutes to. So write down this question and solve. Then you just raise up your hands. At least this one, everybody must solve. Let me see. Some people are dormant in the class. Let's see. So if I didn't hear your voice today, I'll be calling you to give me the answer. So just write down this question. Follow the same approach and solve. I added a question to read the last one. As I've changed the mass to hot to be in hot gram. So make sure you do that one also. I've changed the mass to be in gram, and the temperature also changes to, let's say, 7 degrees Celsius. So you are no more going to use the 5 degrees Celsius, you use 7, and the mass of 300 grams. So use the mass of 300 grams. And I told you that if the mass is given to you in gram, you have to change it to hot kilogram before solving. So the second question having two aspects. You find for the quantity of heat or the heat supplied or the heat energy used using the mass 5 kilogram, temperature 5, and the specific heat capacity of water to be 4,200. If you get that one finished, this is another set of questions, but link up to what link with what the question 2. So by the question 2, that's the II of the question 2. So the mass is 300 grams. make sure you change the gram to what kilogram. And the temperature is what 7 degrees Celsius. You are going to use the same specific heat capacity of water, which is 4,200, to solve. So in all, you are going to get about 3 solutions. Okay. Yeah. Alate.
Sir,
Yes.
please, the first one I got 1,380,600 joules per kilogram degree Celsius.
It's not if the figure is very high, make sure you use the prefixes and things, okay? Let's say you have 1,000. So for you to just be on the safer side, you just say 1 kilo, 1 kilo. Okay. Okay. Because
Okay.
kilo is 1,000, or mega. You can use mega also if the zeros are hot. Let's say 6. Okay. Any you said the first one is what?
1,308. Sir, wait. Oh.
Hey, the rest are still solving. Avuglan.
Sir,
Yeah, I'm listening now. Yeah.
sir,
For the first
138,600
one,
joules
I had 2.
per kilogram degree Celsius.
Kilogram. Hmm.
Degree Celsius.
Okay, yeah. Where you have to calculate the quantity of heat supplied or stored. Anytime I ask to calculate the quantity of heat, the unit of for the quantity of heat is what? Joules. Joules. If you have to calculate the specific heat capacity, the unit is what? Joules per kilogram per degree Celsius. That's specific heat capacity, the unit. If you have to ask to calculate the mass, the unit is what?
Okay, sir.
Kilogram. If you are asked to calculate the temperature, the unit is what? Degree Celsius. Okay, Kenneth.
So please, the first one I had 26,400 kilogram per degree Celsius. And the second one I
24,000.
had
Okay.
6.
Okay, the second one you had what?
The second one I had 105,000.
105,000.
Yes.
Oh, okay.
And the third one I had 8,820.
Okay. Let's listen to another. Justin.
Sir,
Yeah.
so the first one I had 26,400 joules
Okay.
as the amount of heat stored. And then the number 2, I had 105 kilojoules.
105 kilojoules. Okay.
Yes, sir. And then the third one, I'm not sure, but I had 97,020 joules.
Okay.
I'm not sure of that one, but
Adiabo.
So the first one I had 26.4 kilojoules. And the second one I had 105 kilojoules. And the third one I had 8,820 joules.
Okay. I'm coming. Let's verify something. Let's see whose answer is correct. It's then- Okay. Hope you can see us on the screen. So the formula you are going to use for the first one,
Yes.
the first question, the formula you are going to use is the same for all. It's the same throughout. The Q is what equal to what MC hot theta. And we know the M to be hot 0.6. The C is what the specific heat capacity, which is what 800 times the theta. The theta is the temperature difference, which is what 75 minus 20. Was it what you guys did? So 0.6
Yes.
times
Yes, sir.
800 times 75 minus 20. What's the answer?
2,000.
26,400 joules.
26,400 joules. Okay, that's good. So you are going to
Yes,
Yes,
sir.
sir.
yeah, you are going to use similar approach for the second one also. But the second one, they've just given you one temperature, so you are going to use the 5 just like that. Okay, you are not going to subtract it from anything again. So
Okay.
it's going to be
Yes,
5
sir.
times 5 times 4,200. 5 times 5
200.
times 4,200. Then you get your answer. But the third one over there, you have to change the 300 to what? Kilogram. So you divide it by what? 1,000. Is that not so?
Mm-hmm.
So 300 divided by 1,000 to get the kilogram value. So it's going to be 0.3. So the mass over there is going to be 0.3 hot kilogram. The temperature is hot 7, and the C is hot 4,000 hot 200. So you multiply
That's a mistake I made.
the 3. That's what 4,200, which is the C. The mass is hot 0.3, and
Okay.
the temperature is hot 7. Okay. So that was it. When we meet next time, we are going to talk about the sensible heat, latent heat, and we'll look at how to calculate the sensible heat, how to calculate the latent heat. We'll look at the two types of latent heat. That's the latent heat of fusion, latent heat of vaporization. So that's what we are going to do next time. So make sure you read ahead of time before we meet next week. Thank you very much for your time.
Welcome, sir.